if you're cold, just say something. I will try to switch on. To switch off.
Yeah, so I guess I get to finish Ricardo's portion of the program, and this will be a little bit further afield from a lot of what we've been hearing today and these last 2 weeks. I am very strongly tried to get rid of as many Feynman diagrams as possible and tell the story from a much higher level. But the threat will be that if you don't ask enough questions, and if I have to fill the gap at the end, the Feynman diagrams and the Feynman integrals will come out, and things will get a little bit hairy. So yeah, I'll be talking about effective field theory descriptions of gravitating binary systems. You might summarize that with less jargon as we're going to solve the two-body problem in GR. So Ricardo was telling us earlier in the week that when we're looking at binary black holes, binary neutron stars, other objects like that, that while gravity is very linear at the detector, it's extremely nonlinear at the source. We're going to go and start deriving that nonlinearity at the source, looking at various different approximations that are useful in different ways. Since this is a very new group of people that I'm talking to, I like to do an introduction slide for myself. I'm Alex. I did my PhD at UCLA, first postdoc at Uppsala University, and I'm currently at Northwestern. My experience is primarily in particle physics and formal particle physics at that, with lots of multi-loop stuff in supersymmetric Yang mills and supergravity. If anyone besides Ricardo and maybe Rogerio knows the connection between these three places, you get bonus points. And after playing around a lot with these multi-loop methods, now I'm exploring various applications, as we'll see here, in binary black hole and in gravitational wave physics, and moving a little bit towards EFT of LSS. Now, you might say, what is a particle physicist doing studying binary black holes? And even longer term studying EFT of LSS stuff. And essentially, it's a lot of toolkit stuff that crosses over. So I'll start with the question, what are the fundamental properties of a black hole? In GR, what describes a black hole? We'll open to the audience. Mass, spin, charge, yay. What describes a fundamental particle? Mass, spin, charge. As I said, that means there's a very similar toolkit, depending upon exactly how you phrase the problem, to talk about these two types of systems. There are a bunch of subtleties, and actually some of the subtleties are related to in-related formalisms. But a lot of the tools carry over, a lot of the tools have direct analogies, and a lot of the tools can be very informative about how to actually approach binary black hole, binary neutron star problems. So I'm gonna start with a very broad picture. The central driving idea between taking theoretical and numerical predictions and turning them into things that we can actually compare against data is this effective one-body formalism. It is a black box for all intents and purposes. It is essentially a central force approximation with a bunch of corrections on it. And in the end, you get out some Hamiltonian where you can do standard equations of motion and standard calculus of variations to get out predictions for various gravitational wave things. But there's a bunch of parameters in there that you have to fix either via numerical relativity, which is a computationally expensive, very painfully computationally expensive process, or using perturbation theory. The nice thing about the EOB from the perturbation theory point of view is it actually does a little bit of resummation of various terms, but in some very difficult to understand and difficult to track way.
But there are other phenomenological ways to process the fundamental input into a waveform.
Yes, yes. So this is one of the standard ones. There are other ones as well. This is the standard at LIGO.
I would say one of the two main standards.
Okay. And from there, then you can start rapidly producing templates. I guess this one built in like a second on my laptop. So once you have some of this under control, you're good to go. But because of some of the resummations, the nonlinearities of stuff in here, saying what order in perturbation theory do we want versus how many numerical simulations versus whatnot to get precision on the backside is a complicated thing. So we're just going to delve into how do you push perturbation theory as hard as you can in various directions, and what comes out, and how do we do it. So the first thing we need to think about is where are we actually doing perturbation theory? So the primary source that we have for gravitational waves, well, I guess not anymore, now that we have our pulsar timing arrays producing fantastic data. The other primary source that we have for actual point sources is binary black hole mergers. So an idealized merger looks something like a very long in-spiral phase where the objects are well separated and slowly infalling towards each other. And this is a long, nearly sinusoidal signal. Then there's the merger region, which is where the horizons get very close, start to touch, and finally a ring down. So the Inspiral, as I said, long time scales, long wavelengths, small amplitudes, and a nearly circular process for the most part. This is very amenable to various perturbation theory schemes. Merger is a very short time scale effect. This is where you run into things that are extremes of GR. There's most of the energy is lost in this region. And this is the really hard thing to touch with any sort of perturbation theory. The horizons you're touching, you get extremely model dependent. If you want modified theories of gravity, if you want things involving quantum gravity, don't touch this with perturbation theory. This is very much in the realm of numerics for now.
Can I interrupt?
Yeah.
In your template in the previous slide that you showed, you said that in your laptop, you do have this merger region at the end.
Yeah, so part of the EOB, part of the resummation that happens in this black box that is EOB allows you to push it closer to merger than you might expect. But the EOB template does also take input from numerical relativity.
So you're taking input.
So there is some input that comes in from numerical relativity that is used to fix some of the parameters in EOB. Some of it comes from perturbation theory. This is resumming a lot of different predictions that come from both analytic and numeric methods. So merger, we're gonna do our best not to touch it with perturbation theory. Then on the backside, you have the ring down once the two objects have become a single larger object, and it has to relax down to a static black hole state. Here you can use other forms of perturbation theory, black hole perturbation theory, quasi-normal modes, but it's effectively a one-body problem instead of a two-body problem. So as I said, I'm going to be focusing on the in-spiral phase. This is also a worthwhile thing to look at long-term because objects that are going to be sitting in LISA band are going to be sitting in LISA band for tens of years, hundreds of years. Basically, as long as LISA is turned on, we're going to have signals sitting in there. And these are mostly going to be, well, depending upon what signals you're looking for, are going to be primarily in the in-spiral region. And their accumulated phase shifts are very important to keep track of. Actually match up your signals with your parametric templates. So getting really good at perturbation theory to pull our information back down along the in-spiral phase is rather important. And one of the reasons that analytics is helpful for this is that numerical simulations are not so good at pushing way back in the in-spiral phase. I don't have a good graph here, but a lot of the calibration curves that are used for the templates, they cut off where the numerical relativity ends. And it's essentially just because the simulations get more and more expensive, and the more cycles you do in numerical relativity, the more you accumulate numerical errors in addition to whatever other systematics you have. You lose control very quickly as you go for longer and longer and longer cycle durations. So I phrase this as an EFT description, so I should talk a little bit about what we mean by effective field theories for these systems. And the basic idea is that we're going to have some collection of body details. And don't think too hard about this because we're going to ignore it very soon, but there's going to be some collection of body details that some microphysics of your theory, whether that's descriptions of the black hole states through whatever description of black holes you're going to use, some neutron star equation of state, equation of matter, all goes into some body details. If we know those theories exactly, we could sit down and we could work out how those body details turn into effective descriptions in terms of multipoles, spins, and tides. Then we could take those terms, turn them into a two-body problem. From the two-body problem, we can look at either the conservative dynamics, which would give us things like the orbital frequency or the periastron advance, or the radiant dynamics, which would give us things like the radiated energy or the waveforms at infinity. Now, we really don't want to actually think about the body details. These are extremely model-dependent things. So we don't want to explicitly think about, oh, what does the microstate of my black hole look like? What are the thermodynamics? Is there a firewall? That sort of thing. We want to ignore that as much as possible for actually getting efficient predictions. Similarly, the neutron star equation of state is something that is under a lot of debate. And the actual hope is that we can turn this entire process around and say, oh, we know from just doing the gravitational wave physics how it back propagates to things that would talk to the neutron star equation of state. And so we can turn the entire thing around and say, we can solve this whole problem in the box very well. And we can use those, the solutions and the measurements to then constrain things about the body details in the end. So this is our approach to effective field theory, that we're, in the language of effective field theory, we're integrating out the details of the body and then progressively integrating out more and more stuff as we get closer and closer to the actual observables. Then we can turn it around and say, we now have this IR theory, which is GR and the gravitational waves from GR, and match them against whatever our UV theory is that describes the individual bodies. So there are three primary ways of doing perturbation theory that are centered around the Inspiral. The first is what's known as self-force theory. You might have just heard of this as black hole perturbation theory, and the two communities are very close to each other. And the idea is that you have some heavy object that you take its metric as given. So often it's going to be Schwarzschild or Kerr, but potentially some other complicated thing. You have some heavy object, you take its metric as given, and then you have a small object that you're perturbing the geodesics based on its own back reaction. I'll talk a little bit. I will be talking progressively more and more about each of these as we go through the talk. The next style of perturbation theory is post-Minkowskian. This is where we're perturbing around weak fields. So we take a static, flat Minkowski background, and then gravity is some weak perturbation on top of that. This is effectively, as long as the objects are well separated, but we allow them to move arbitrarily fast, well, relativistically fast. Finally, there's the post-Newtonian approximation. So this is where we do a perturbation both around slow objects as well as weak fields. So we assume that the objects are well separated, and we assume that we're in some primarily non-relativistic regime, and essentially somewhere where the virial theorem can apply. And so we have some equivalence between the velocity of the object and the potential energies of the objects. Now, why do we need all these different analytic approximations? Well, they cover very different areas in parameter space. So we have a couple of comparisons between mass ratio, periastron distances, and eccentricity. And we can see that self-force is very good, as we might expect, where there's some large mass ratio, where it's very much true that there's one big body, and that big body doesn't feel the small body that much, but you really care about the small body motion. Versus post-Newtonian and post-Minkowskian, which are much better when they're equal or equivalent mass objects. But the post-Minkowskian and post-Newtonian separate themselves. Post-Newtonian, as mentioned, is very good for circular orbits. Post-Minkowski is very good for elliptical orbits and for hyperbolic approaches or scattering. Yes.
What do the colors mean here?
The colors are just doing some gradient stuff. Yeah. There's not, it is just, post-Newtonian, post-Minkowskian is the purple color on this one. Sort of up in this corner is where you can do cross checks between self-force and either of those. It's vibes.
But what, so post-Minkowskian breaks down at low eccentricity for circular orbits, that they say?
Yes. And the reason is because post-Minkowskian is assuming that your background metric is the flat metric. And for that, you need to be able to widely separate your initial states, essentially. This is a bad approximation if you actually have a circular orbit, right? Where are your two states far separated?
But, so that also applies to spiral orbits, right? Because slowly spiraling circular orbits, it still means that you cannot apply it.
Yes, yeah. So slowly inspiraling circular orbit means post-Minkowskian is not a good choice. Right. But
Okay.
yeah, but there are the place where it actually breaks down is relatively deep in perturbation theory. And so there are like the lower orders of perturbation theory, you can actually sort of map the back and forth between the two, and the effects you care about to distinguish between these problems of external states are sufficiently suppressed in perturbation theory.
But we expect high eccentricity, binary orbits in general, so that it would be a good idea to go to post-Minkowskian.
We do there is a lot of post-Minkowskian, yes.
Yeah, no.
No, like from an analytic perspective, we are very good at doing that already.
Yeah, but real nature, do you expect high eccentricity for this binary black holes?
So early on in the Inspiral potentially, but for the binary systems, not so much. There are people that are starting to look for transient scattering events. And then post-Minkowskian is exactly what you want when looking for those sorts of things.
So this feature, I mean, I had a picture that supposed Minkowski was just receptacle.
And no, it's not. In certain situations it can be, but it is not just resummed. And part of that is just that there's again with post-Minkowski, there's some assumption of well-separated external states. And that only holds so far in matching with a resummation of post-Newtonian.
Parallel with the electrodynamics, because when you have two charges which are not that's particle, they both
Yeah.
contribute to the field.
Yeah.
Then solve the Maxwell equations coupled to Lorentz equation, and it's very complicated as well.
Yes.
So
Yeah.
there are parallels that you can make.
Yes, and actually there's a good chunk of the field who's trying to make that parallel essentially exact. It's a somewhat challenging problem, but it is something I can get into a little bit more. There's what's known as the double copy, which people are actually very hopeful that you can literally take an electrodynamic system, do some operation to it, and you get out one of these gravitating systems.
I mean, even he's talking about QCD actually now, where you have self-interaction of the gauge fields. But even aerodynamics where you don't have self-interaction, so that's a simplified form of gravity. It has basically all of the grids apart from the self-interaction of the gauge bosons. It basically has all of the grids. You can solve the two-body electromagnetic electrodynamic problem.
With fast particles.
I mean, I mean, fundamental particle, any charge, any mass, and basically you can use it as a test ground for all the methods of gravity because it's a simplified gravity, right? Gravity.
Yeah.
So if you can solve electrodynamics, I mean, if you can solve electrodynamics, then you are likely to solve gravity too.
So someone, I think Miguel mentioned about high eccentricity. You were saying, I don't know, please correct me. The entries, the orbits are quite irregular, aren't they? So it's an opportunity to see some where high eccentricity is important.
Well, Emily's
Emery's live more in here, and so Emery's are actually really well captured by self-force.
no matter eccentricity.
Yeah, no matter the eccentricity, you don't have to go over into the post-Newtonian or post-Minkowskian to get a good idea for Emery's. Self-force does a good job. Also, this is a good chart for pointing out why you can't just do simulations, because numerical relativity, again, is very hard to push away from close to the origin of both of these plots. There are actual computational limitations that you run into and insurmountable ones in the end with things like floating point error accumulation that prevent you from getting too far away in various regimes.
So the rotation expected to be surpassing in the future, or is
I have very little information other than knowing that it is a problem to go to various places in parameter space with numerical relativity.
surprised by that, the numerical region is confined.
So part of it is that like if you have very far separated bodies, accurately modeling the gravitational interactions between the two becomes prohibitively expensive. So the further apart they start separated, the more costly it is. And I believe in a nonlinear way, but I haven't.
Basically, you have three scales you have to monitor: the size of the black hole, the separation, which by Kepler's law is size of the black hole divided by v squared, and then the wavelength of gravity, which is separation divided by v. So when the separation is large, v is small, you have one scale, 1/v squared that scale, and 1/v the previous scale. You have three scales that are widely separated. So you have to use the basically your lattice has to be smaller than the smallest scale, and to monitor the large scale with the lattice which is smaller than the small scale, you basically
Can I ask another question? So on the eccentricity, if you have gravitational waves being emitted, does that affect your eccentricity? Does it go down?
Yeah, so this is essentially one of the circularization.
Yeah, it does, right?
Yeah, so you will get for very eccentric orbits, you get bursts of radiation as you are very close, because again, it's essentially the kinetic energy that radiates.
Yeah, so could it be that you can do an expansion that you start post-Minkowskian and then you flip to post-Newtonian as the eccentricity goes down? This makes sense to do something like that?
There are probably various ways of doing that. I don't think anyone has looked significantly into these sort of explicit matching situations. But EOB and these other EOB is sort of designed to try and do this for you, to pull together all this information in some effective description, some net effective description of everything. Yeah, I'll leave it at that.
But just to clarify,
Yeah.
but the reason for you need post-Minkowskian for high eccentricity is that the speed of your circle of the orbits get larger.
Yes, yeah, at the closest
yeah.
approach, you're going very
Yeah,
fast.
so,
Yeah.
But formally, post-Newtonian is a particular case of post-Minkowskian.
No. So again, there's this external state problem with post-Minkowskian versus post-Newtonian. So post-Newtonian is doing some adiabatic approximation where you don't really have to worry about initial and final state separations. In post-Minkowskian, you do to some extent. And so there is eventually a breakdown that prevents the two from being exactly equivalent or exact resummations. And I will also add that the problem that Ricardo mentioned about having these multiple scales for numerical relativity is actually exactly the thing that makes this super amenable to an EFT treatment. Because you have these, EFT says when you have these scales that decouple, great, that's exactly what you need. Okay, so we'll go on and discuss these all in a little bit more detail. I'll move quickly through self-force because it's the one that I have the least direct knowledge of. The basic idea, again, is that you're expanding around deviations from geodesics. So you have some mass ratio, and you're taking that mass ratio as the thing that's very small. And the idea is you start with some background metric G, which is going to be some exact metric in terms of the large body. Again, Schwarzschild curve, potentially more interesting things, and then expand it in terms of corrections, where the corrections are addressed with mass ratio. Then you just iterate the solutions to Einstein's equations. So just as a strong statement, you iterate the solutions to Einstein's equations by plugging G and small g and Gothic G back into the equations and start solving them order by order in the mass ratios. So the thing that happens is that at first order, everything's fine, everything is sensible. If you plug in a point mass, you get out something that looks like a 1 over r potential. Great, fine, everything solves. You try and go to the second order, and you run into all sorts of problems. Essentially, it's tied into the fact that your second order perturbation, in terms of the first order perturbation, means that whatever distributional thing you have describing your point source now is like an m squared over 4. It's very bad. You do not want to try and do any predictions with that. It's not an integrable distribution, not an integrable source in any sense, including as a distribution. There are a bunch of ways that this community has worked very hard to formally address the problem. All of them in the end point you to, even if you start with the point particle is not a sufficient description at higher orders. What you really need is a set of multipoles that are sitting wherever your small body is. So even if you want to start with a point particle, the back reaction with the metric turns it into a set of multipoles, forces you to go to a set of multipoles.
Sorry, first order, what you meant there is that analytically you can address.
Yeah. So first order, if I just plug in a delta function, essentially I plug in a delta function for my stress energy tensor, and I work it all through, and my fields will go like m over r, totally fine, totally reasonable, as you might expect with Newtonian intuition. But then when you go to second order, effects compound on themselves, and now you get some field that is not happy, not integrable, and so it is not something that well represents even a point charge.
But for example, the scattering angle,
This is before even talking about observables. This is as you start looking at the behavior of the field. The field itself is very poorly behaved if you force it to just be a point particle.
I do think so. You have the method that you're putting is like some central protection kind of thing.
Yeah, so it's the exact metric for a black hole.
Okay. Or curve or.
So yeah, so Schwarzschild curve or whichever you want.
And the thing that you're perturbing is because I thought that you were having like this particle that was modifying its trajectory. So are you?
Yeah, so we're saying that the entire metric everywhere in space it starts from the geodesic, like the background metric, of the big body. And then there are induced corrections because you have a small body, and the small body now has a
Back reaction.
now it has an untrivial mass, and so back reacts on the metric.
Okay.
Just making the analog to electromagnetism. You have so higher order over R expansions and just need to sort both.
Yeah, no, exactly, yes. It's just that it is more complicated to formally establish that in GR. But yes, there are, I think even this review that I've cited there even starts off with electromagnetism as a motivating example. Yeah,
The idea is the same.
Yeah.
It's nothing else but higher multiples.
exactly, yeah. It is just amusing that as long as you start with a point particle and you are forced to introduce multipoles. Okay, so again, going to be very brief on this part. The state of the art for self-force, the goal is to get to second order in self-force. As I said, this is where the actual problems kick in. The progress in that direction is that essentially 1SF is solved. I guess for this community, it's definitely solved that there are semi-analytic packages out there that can do more or less whatever observables you want out of whatever reasonable spacetimes you want as your background metric for 1SF. They have made progress on 2SF. And as you can see in these two plots where the dashed lines are very faint, and that is not my fault, that is the review plot's fault. The 2SF actually does a significantly better job of reproducing numerical relativity in these regions of interest than either the 3.5 post-Newtonian or the first self-force. And this is actually a fun one. So this is Q equals 10, where you're relatively strongly in the self-force regime. This is Q equals 1, which is actually kind of funny that you can actually get very close to good results, even in the situation where your approximation is starting to break down a little bit.
So but why the flux go down? Should increase. So what is the x-axis?
The x-axis is the post-Newtonian x.
So why doesn't the flux grow with x?
That is a good question, and I do not know the answer to that. But it is tracking numerical relativity.
Maybe some renormalized flux.
Yeah, something like that.
So you are taking as they go out through the issues from numerical relativity.
Yes.
So then I don't fully understand the discussion that after, like, because what I understood from the other code, the gradient color code is that there were certain regimes that you needed to take other approaches different to numerical relativity due to these scale arguments. So how come that in here?
Yeah. So this is like in the overlapping regimes.
Okay.
So you can say you can do all of these you can do various analytic methods, and I say, okay, if I evaluate them in the overlapping regime of validity, where my analytic approximation is good and where there's numerical GR data, then you can start doing matching or comparisons like this.
So in the general framework, the way in which the people validate the different approaches for doing perturbation with this is like overlapping with numerical.
Well, essentially you overlap with as many different things as possible. Yeah. So you try and overlap with NR when you can, and you also, because these are all just different approximations of GR, you should be able to re-expand your other variables. So for instance, you can take self-force results, re-expand them in G also, and that should land you on very specific pieces of post-Minkowskian. You should be able to plug in circular orbit conditions, your self-force, and then you'll be able to extract post-Newtonian corrections. And essentially, you can think of like self-force doing some resummation of post-Minkowski with some other parameter kept small, or similarly, post-Newtonian with some set of parameters with some other set of parameters kept small. So you can always do the other expansions and check between all the different theories, even when you don't have access to numerical relativity. And yeah, so because it ends up being very similar to black hole perturbation theory, this community crosses over quite a lot with them. And there's been some recent developments of working along this cross expansion line to try and figure out ways of getting a Feynman diagram and more manifest the EFT description for these problems. Okay, now we can change gears a little bit. We're gonna go to post-Minkowski instead. So instead of expanding in mass ratios, we're gonna expand in the metric perturbations. So this is starting with flat Minkowski space, and then we have some small perturbation on top that is our gravitational interactions. If you think about this a little bit, this is actually sort of exactly the thing that is analogous to particle physics. We have a single small term that does some self-interactions, and as long as we're careful with tracking all of those things, this is just standard like relativistic field theory, where it's the metric that we're perturbing, but don't worry too much about that. We're still perturbing on top of flat space. So this is where we really get to leverage a lot of the tools that are coming out of QFT. So you can do Feynman diagrams. If you don't want to do Feynman diagrams, you can do some of the more advanced stuff, which is using on-shell methods. You get into the weeds very fast with integration and Feynman integral problems. And up until very recently, you do not want to do Feynman you do not want to do Feynman integrals numerically as much as possible. This is starting to change. There's been some very powerful advancements recently. But regardless, there are a bunch of analytic techniques for handling even horrendous multi-loop, like 3-4 loop Feynman integral computations. The basic idea with the post-Minkowski EFT is that you're going to compute some classical scattering amplitude, and you're going to match that onto some iterated hyperbolic potential, hyperbolic encounter Hamiltonian with a two-body interaction potential. So we can simplify that as we have the energy of body one, the energy of body two, and then some Gn over R scaling potential, where each of the coefficients is dressing higher and higher powers of G. And you take whatever you compute here, you match it up against here, and then you can use that to fold back into either the EOB or do direct predictions, direct observable extraction, because this is a Hamiltonian. You know how to do stuff with Hamiltonians. And the basic setup for this is very nicely captured again in the particle physics language. So the simplest case is that we have some spinless black holes that are interacting with each other, these binary short-shell black holes. And we just model those as massive scalars. Again, what do we have? We have charge, spin, mass. The mass we don't really have to worry about. That's all baked into the particle physics language already. The spin we're setting to 0. This is a very complicated topic that I will not talk about, so we're just going to set spin to 0. And charge, no charge yet. All it's doing is interacting gravitationally. But we have this nice hierarchy of scales. So for especially the lowest order stuff that we care about, we're going to be caring about some potential zone where the energy of the interaction, the energy of the interacting gravitons is very small. That is, they're potential gravitons. They're essentially instantaneous. And then also we're going to care about some classical only expansion. Because if we are not careful, we might accidentally allow quantum effects in. But for those of you who remember back to QFT, what's the rule of thumb for making sure you don't have quantum effects when you're doing Feynman diagrams?
H bar.
H bar is a great starting point. What does H bar imply?
Loops.
H bar implies loops. How many loops have I drawn? I've drawn a lot of loops on here. So there's actually a more refined argument that it's if you do the H bar counting very carefully, it's not loops that are the problem, but it's massless loops that are the problem. So you want to make sure that you have no graviton loops, and that's essentially what this expansion is doing. So no graviton loops, but you're allowed to have loops where the gravitons connect to the external matter. That's totally fine, and this is essentially just iterating. Let's go back here. This is exactly the sort of loops that show up here, where you're just iterating a two-particle interaction over and over again. So that's totally fine from the point of view of classical physics. We're going to throw out all the quantum stuff, so no graviton loops. We don't have to worry about quantum gravity. Now, as I've drawn here, this essentially gets you all the conservative stuff. If we want to go to radiative stuff, now we have to add either an external graviton, or there are ways of extracting radiative information by doing self-energy computations, which is where your black hole diagrammatically emits and then reabsorbs some graviton. But you can do some tricks with the integrals and taking discontinuities on your integrals to open that graviton up and turn it into statements about radiation instead. So, yeah.
But then, why can you not have closed loops which are classical from this gravitons?
So as soon as you have closed graviton loops, those end up becoming, those do have quantum effects. And there's a very nice formalism called the K-Mach formalism, which does a very good job of demonstrating the fact that closed graviton loops will always end up producing quantum results. Will always, or will at least always end up producing results that have an H bar on the front. So that when you take the H bar goes to zero limit, they drop out.
One ingredient to understand this is that where in the loop you have a propagator of the particle, of the massive particle, actually you should take the M to infinity limit. And basically the M to infinity limit kills the H of that loop. So it becomes a classical loop. So the thing that I guess you are my, so when you learn quantum field theory, it was told that any loop is quantum, it's simply wrong.
No, for sure.
The loops have both classical and quantum contribution. And the classical part is the only one that survives when you send the mass to infinity. But if there is a loop of graviton, there's no mass to send to infinity, so it's purely quantum.
Yeah, so this thing will go like H bar, whereas this will go like 1. And so when you take an H bar goes to zero limit to extract classical, this thing sort of manifestly drops out.
Yeah. And angular momentum by the black hole is 10 to the 70 H bar.
Yeah.
I mean, that effect is quantum is there, it's physical, it's just that it's smaller.
Yeah. I guess like presumably semi-classical gravity is also very well defined. So couldn't you at least keep like the first contribution of the bit if it's large?
No, but it's 10 to the minus 70.
No, sure, but in a regime where it is actually large, it's not an issue to have these H bars at least to.
No, yeah, it is not an issue. I mean, you do then have to start getting into questions of like, what is the UV completion? That at least while you're in the classical stage, you're not worrying. You're not worrying in particular. All your UV divergences are microphysics things and are not actually like gravity itself being divergent.
Mm-hmm.
So this is helping you stay away from string theory.
That confuses me is that, okay, you're doing, everything is classical, you start with the Newtonian, you do this classical equations.
Yeah.
I would see why you will not end up with closed loops, yes, with gravitons, we're doing that. But you're saying that no, you will never get, or if you get, you have to.
Yeah, so that if you are tracking things through very carefully, anytime you get a closed loop of gravitons, even if you're starting from like a Hamiltonian and iterating it, if you think about, the degrees of freedom and the scaling separation, anytime you see anytime you get a closed loop of gravitons, when you rewrite it in the correct variables, it will pop out a factor of H bar, and it will always be H bar suppressed compared to the leading, this stuff with no graviton loops.
This computation could have been done by Laplace in.
No, I mean, there are papers in the 80s, they compute the quantum correction to the two-body problem. They are physical effect, they are there, they're just ultra small. But if they are physical and they are known, it's written in papers. They're just ultra small.
Yeah, LIGO will never see this ever. LISA will never see this ever. Pulsar timing arrays will never see this ever. These are realistically zero computations or zero contributions. Okay, so PM started off rather slow because again, it's not as great of a model of the Inspiral phase. So there's some older results from the end of last century. Oh, that's a weird thing to say. Still 25 years in is a weird thing to say. So there's some older results from sort of the end of last century where tree level, okay, it's tree level. Hopefully everyone remembers enough, at least classical field theory to do tree level calculations. And you get out some very simple results. In fact, if you do the electromagnetic calculation for the counterpart, this thing is almost exactly the square. You have to fudge it a little bit, but you can square the electromagnetic results and get these results. You can also go to one loop, which is second post-Minkowskian. Okay, everything is still rational. That's good. That's great. That's fine. And then recently, there's been a renaissance in the post-Minkowskian as particle physics people have come over, jumped ship, and tried to claim as much space as possible. So this is I believe, 2018 result from some of my former colleagues at UCLA. And this is now a two-loop computation. So 1, 2, 0, 1, 2 loops, and we've got a 2-loop ladder plus a bunch of other diagrams there. And when you go through the entire computation, you'll find out that this C3 has an arc cinch on it. Yeah,
Or just like morally looking at the diagrams you're drawing, it looks like there's only a single like one PI irreducible diagram. So like you're just like pasting multiple copies of the same diagram on itself.
So for these early ones, yes,
Uh-huh.
there are inside the 6 more.
Okay.
There are more involved ones. So I think at this loop order. There we go. There's like this sort of diagram that shows up at 2 loops. And so that is not just some iteration diagram anymore. And especially as we go to 3 loops, there are now lots of diagrams that are not just iteration diagrams. However, the iteration diagrams are a special class that are known as the iconal approximation. And there are groups that work specifically on understanding those a little bit better.
Have people try to resell them presumably?
Yeah, to some extent, yeah. So certainly the leading ladder diagrams, and I believe their friends have been resummed. And people are working on I believe the second order of that. So this group also continued on, did 3 loops, and now there are a couple of other groups that have done this as well. So there's 3 main collaborations that are working on this post-Minkowskian front. There is the UCLA and Caltech group. There's the Humboldt group, and there's Rafael Porto's group in DESI. Rafael's group. So again, we get much more complicated diagrams showing up in here. I'm going to dot it completely because now it's very hard to even gauge effects, make it very hard to even count the right number. We have iterated stuff. And the reason people haven't gone further, the reason I'm not saying, oh, there's a C5, is because when you hit C4, you get elliptic kernels. You get E and K functions. You get the polylogs are fine, but the E and K are very annoying. And going beyond that, people are afraid that we're going to hit. That we're definitely going to hit more elliptic stuff, and better understanding elliptic integrals is a very hard problem. And going even further, there will be stuff like Calabi-Yau integrals showing up. Yeah.
Does one find the divergences at these orderings exponential or?
I would have to think a little bit about that. I believe all the divergences are under control. Like that, there are loop-related effects and there are cross cancellations, and this is all done at dim reg. In the end, we know how to handle all of the dim reg related stuff that we run into. So everything, all of the results they have are if there are divergences, they are all removed via the normal particle physics, like dim reg, renormalization, regularization procedures.
So those different groups proceed through different approach, right? So what
Yes.
Rafael is doing is basically this bound story, right? So
So that's a slightly different story. So that is the story of how you get from these to post-Newtonian.
Right.
But yeah, the other, one of the nice things about having 3 collaborations working on it is that there's sort of 3 different flavors, 3 different frameworks, 3 different problem-solving strategies to approach this. And so they actually, there's very strong cross checks between all the 3 groups.
can you describe slightly what's the difference between what those groups are doing?
Ooh, let's see. So I know, so the Hamburg group, or not the Hamburg group, the Humboldt group is doing what they refer to as worldline QFT. So this is a idea that they've been exploiting, which is that you do somewhere between worldline methods and QFT methods, and are careful about what types of propagators and what types of matter propagators you actually care about integrating versus you don't care about at all. And theirs is particularly useful for doing spin because you can encode at least the first couple of spin degrees of freedom as a supersymmetry on your world line. The UCLA group is doing unitarity methods, so doing on-shell methods with cut sewing and that sort of thing. It's involved, but is a very gauge invariant approach to things. And I don't remember what Rafael's group is doing. I think they're more on the worldline QFT angle, a little bit closer to that, right?
Yeah, and they have a very effective approach. I mean, they don't even, I mean, they really focus on observables. and they can compute observables much straightforwardly, bypassing somehow the dynamics.
But the real thing is that all of them eventually hit this problem. Sort of no matter what you do, you're always stuck eventually doing annoying integrals. And those integrals are very quickly outpacing how fast mathematicians and the QCD community kind of figure out ways to actually do them.
So the problem then is then we don't have a mathematical basis to define those integrals in terms of analytical function.
Yes, essentially. Yeah, you can project down onto the master integrals, but turning the master integrals into an actual function that you know how to evaluate is a different story.
So this field is kind of defining new functions as integrals.
Yeah. Well, I wouldn't say this field in particular, but there are people who are experts purely in Feynman integrals, and they are in the process of defining all these new functions. So like elliptic integrals have been known for a long time, but the properties of things, like if you're starting to integrate and you run into integrals that are relatable to Calabi-Yau manifolds, those are not well understood at all. I say that, but like 3 years ago, Claude Berg, who's a very famous person in the field of integrals, got up, gave a half-an-hour talk and said, here's how we do elliptic integrals, and then said, now replace every single time I said elliptic in the previous slide with Calabi-Yau and everything goes through fine. So there's some substantial progress, but there's still difficulty. I mean, turning these things into like numerical evaluations to actually plug into some templates is still a long ways off, but we're getting better understanding the analytics of it.
And the number of diagrams, is it the
So the number of diagrams here is relatively tame. It's double digits. But the number of individual integral contributions is, I have heard the phrase 1 million thrown around with respect to how many integrals they get out before reduction. Okay, so just to point out real quickly that even though post-Minkowskian has this problem with properly approximating post-Newtonian, if you feed it through the effective one-body formalism and use it to use post-Minkowskian to fix various things instead, you actually do see trending towards either the EOB through PN reference or towards the numerical relativity, depending upon which benchmark you want to use. So yeah, the post-Minkowskian does actually do a reasonably good job up to a certain order of approximating and of fixing the things that we really care about. Ricardo making faces at this.
No, is that people might not be aware that actually knowing the Hamiltonian or knowing the scattering angle contains the same information. I mean,
Yes, yeah.
the scattering angle for a genetic impact parameter for genetic energy contains as much as information as containing the full Hamiltonian. This is a non-trivial piece of information.
Yes,
I mean, now the community knows, but 5 years ago, the community didn't know.
that's true. Yeah.
I guess just like, this is more of a philosophical question. You can tell me to
Sure. Yeah.
answer this after coffee, but it's like very surprising that the community would just believe that there's like black box method that is sort of formal, not really that well formally understood, that just happens to fix so many problems and big results look really good when you map things onto this formalism, and that's the benchmark that everyone uses.
Oh, trust me, everyone in the post-Minkowski side of things is very about EOB. It's used because it is the established pipeline.
But it's just like empirically never failed. No one's ever figured out a failure mode for it, or like the failure modes are exactly well understood.
No, well, I mean, Ricardo might be able to comment a little bit more on that. There is a point at perturbation theory. There is a point in perturbation theory where it's actually an exact correspondence.
Sure.
I have a backup slide somewhere that actually maps it out. I can map it out a little bit better. There is a place where you can say, oh, there is an exact correspondence here. And the setup for it is a pretty natural one, that it's essentially you say, I'm going to map into the central course problem. I'm going to map it and have this radially, essentially that I'm going to care about the radial dynamics and the temporal dynamics, but not about the angular dynamics, and to fix from that. There are definitely a number of people who are less than happy about it, but it's what the pipeline is expecting, and it's what the pipeline It's what is the developed pipeline right now.
Pipeline, you mean like what LIGO ends up using?
Yeah, it is. If you want to go to LIGO, this is one of the two ways you have to process your data, is to get it through this EOB framework first.
You have to distinguish what is fundamental, is still substantial. So the effective one body still describes the system of the two bodies are separate. But since phenomenologically, I mean, the most of scenario of the signal we see comes from the merger and so on, you know, it cannot describe all of the signals. So the EOB black box does the dirty job of inputting the information of the merger and the rest, which is badly needed phenomenologically. So, I mean, the fact that you see, I mean, it's a phenomenological resummation, but it's a way to get the input from the mergering down from numerical relativity, and that's you badly need it to do phenomenology. So, I mean, it's not fundamental, but so what? I mean, it helps you to fill in the information from fundamental physics to do fit to real data. That's all what you want. So,
I will wax poetic about this point tomorrow, because there's no
Okay, so finally, we'll speed run through post-Newtonian, despite the fact that it was the most dense section that I was going to prepare, because it's the one that I at all directly worked on. So for post-Newtonian, we're essentially solving for the system under the assumption that both v squared and the potential are small. This is effectively invoking the virial theorem. This is also essentially the very first computation of gravitational waves, way back with Einstein and his collaborators. So you'd say this is by far the longest studied branch of analytic perturbation theory for GR and for gravitational waves. There was, however, a very nice development at the turn of the millennium, where Walter Goldberger and Ira Rothstein wrote this very nice paper describing a clean EFT and Feynman diagrammatic point of view for doing post-Newtonian calculations. And essentially the idea is that you separate your metric perturbations into radiation and potential modes. Okay, this is relatively obvious, but then you assume that the black holes are sufficiently large and that the transfer of energy, even from these modes, is sufficiently small that the black holes themselves don't back react. And you just let the objects evolve, but you compute the changes in the effective metric just due to the gravitational potential. And the reason why this is a very useful thing to do is because then your potential modes, you can expand them and they become instantaneous with some expansion in their energy over their spatial momentum. And so you actually get to dodge a little bit of the problem that comes along with a lot of QFT loop integrals, that the loop integrals here are significantly easier to do. And this also starts manifesting power counting, because we see that the radiation mode goes like V over R, but the potential mode has a piece that goes like 1 over R and a piece that goes like V over R. And so we can start doing manifest counting where we drop stuff that goes like V over R, or we push to higher orders in perturbation theory. And then again, as I said, we couple it to non-propagating world lines. And what we'll end up finding is that our matter action has our sort of normal kinetic term, but that as you integrate these things out, you get more and more contributions in an effective field theory framework, more and more operators where you get loop-induced corrections to them. And in that way, you actually fill out and discover the types of tidal responses that you expect, but are very hard to write down a priori. Yeah.
Going non-propagating world lines.
So that we're essentially solving it at an instant in time. And then we do this, if you do it correctly, then okay, you do it at an instant in time, and then you shift the energy slightly, and you do it again, and you do it again, and you do it again. But you only have to realistically solve the problem itself once.
Are you going to explain how do you compute this first coefficients, CRA?
Yeah, well, so the CRA end up being they end up being loop counter terms, essentially. So you compute them, you compute a loop, you compute the loop diagrams, which I'll show you in a second. And the loop diagrams will have pieces that look like corrections to this, but also pieces that look like corrections to this. And as in EFT, there is some piece of this that you measure, but it's not just the piece that comes from the loop. It's also that you're absorbing essentially all of your all of your ignorance about what's happening on the body itself gets absorbed into these coefficients as well. And so there's some renormalized coefficient that'll pop out at the end, but you need to handle the loop effects to really unpack all of that. Okay, so there's actually a very nice diagrammatic way of getting it through Kaluza-Klein compactification. So you take your time direction and you make your time direction special. That switches our degrees of freedom just from the metric to a Newtonian potential, a vectorial potential, and then a 3D tensorial potential or tensorial field. These things are all instantaneous. And so they have these e squared over k squared propagator corrections that are each kicking in at higher and higher orders in the post-Newtonian. You get interactions from expanding root GR, the normal place you get them, but now you can do manifest EFT power counting by using these different fields. And so, for instance, at lowest order, you get the sigma field coupling to two derivatives of phi. You get phi coupling to two derivatives of A. And then all the other interactions that you have out of root G, all the interactions that you have coming out of the root G end up at higher orders in your perturbation theory. Then your sources, you again expand G, you get a bunch of various sources, and these are all now manifestly carrying manifest power counting in the V's. You can turn these into a bunch of Feynman diagrams. You can start cranking them through. Let's say this gets us up to 2PN. 2PN was known for a very long time from classical field theory. Gilmore and Ross were the first to do it via EFT or via the Feynman diagram method, and they line up exactly with the known results. And then I will say that radiation-related effects kick in at 2.5PN. So this is where we have, there's a V for each radiation mode graviton, and then we have a V squared coupling that ends up being a 0 at V. So you have to go to V squared. And then these potential modes come together to make sure that you don't have any gauge dependence on the radiation. State of the art currently is 5PN. That is, if my counting is correct, 4 loops. And Ricardo is among one of the groups that has done some of these heroic calculations. And then there's this other group, which is a collection of QCD people from Desi Zoyden. I'll say very quick, well, I will, in 2 minutes, 3 minutes, try and blaze through radiation-related stuff. So as we were walking through the tower effective field theories, we've now done our two-body problem, but we still have the radiation stuff to take into account. So what happens is that if you start computing the radiation modes and then project them out and see what they look like tensorially, you'll see that they line up into couplings of multipoles with Riemann tensors. I mean, this is essentially what you expect. But that means that there's some natural bar zone theory in which you can compute the radiation from these multipoles. But the interesting thing with GR is that because GR is nonlinear, GR has self-interactions, the radiation is not just radiation from the multipoles, but it's radiation from the multipoles then attenuated by interactions with the background potential or with other radiation from the multipoles. So you can rearrange things into the spar zone computation where we have monopoles and then the various multipoles interacting with matter, and they all talk to each other because root G. So for PN radiation, I get to claim state of the art for this. And because of my particle physics background, I'd love to just go out and as far as loops as I can. And so the current state of the art is now tail to the 5th. So tail is where you have a quadruple radiation and then it bounces off the potential at first order. Tail to tail bounces off the potential twice, so on and so forth. So 5 interactions with background potential. This is all done using modern on-shell methods. And I can unpack this for anyone who is interested, but there's a lot of fun Feynman integral and numerical evaluation stuff going on here. I will also say that for higher order multipoles, this is again, Ricardo and his collaborators have the claim to fame here. So they've done arbitrary, I believe arbitrary, right? Arbitrary multipoles coupled to the background twice, which essentially consist of these 3 diagrams. But now you need to be very careful about tracking how many indices you have, and there's some very nice closed form results for that. And And the current thing that we have in terms of gravitational wave self-interaction, which is also sometimes known as the memory effect, is the tail memory order. So this is where we have, I should have a curly line there, where we have two quadrupoles, quadrupole radiation from both that comes together, interferes with itself, and then further interferes with the background before it goes off to infinity. And this has only been done so far in classical field theory from Blanchet, and I believe that's one of his students.
Yeah, but you haven't done the memory.
No, not yet.
Okay.
Yeah, the memory itself has been done a couple of different times by Ricardo and by Raphael's group, and
Yeah.
eventually,
It's not quite finished.
yeah, the memory is a tough one. There's omega equals 0 is a very dangerous place to go. So this is being developed on the EFT side, but yeah. Very quick to recap then. As I was saying, post-Newtonian and post-Minkowskian do have a lot of crosstalk. There are problems eventually with mapping between the two. But just to get some names up on the board for people that have done various things. I mean, we get Newton all the way here, Einstein and friends here, and then progressing down to the early, late 2010s, early 2020s from Ricardo and from the DESI crew, and then the order and G stuff going along there. And I believe at every order, except memory-related stuff, at all the various orders where there's intersections, there's been significant cross-checks that basically everyone agrees, except for memory-related stuff. And that's a very complicated topic. So, final recap.
The color does not mean that it's worked out, right? We don't have 6 p.m. worked out.
So there are bits and pieces of 6 p.m.
Yeah,
worked out. Yeah, so like 60%, maybe more than that.
Not, yeah, way difficult to say. It's a couple of coefficients, but that's the hard ones.
Yeah, so there are partial results at 6 p.m. And I guess depending upon who you talk to, full results.
So
6 p.m. is under debate, but
complete, complete, not even 5, right? Or is it 5 complete now?
It's complete,
No.
but for the memory.
Yes.
But for the memory, and the PM is 4 is complete or not?
yeah, 4 is complete, and they're all 3 groups are working on G5. Yeah.
For the purpose of the templates, where do you want to get to?
I think the actual pessimistic side of things is that none of this is particularly relevant. Like, this is where you need to get. So I believe at least what's currently implemented in the template is 3.5, maybe 4, right?
Yeah, not even 40.
So 3.5. So we're like well beyond what's currently being used.
Okay, but at some point be justified to get to 6.
But then I think there's a
conflicts for.
there is a reason. At 5 p.m. you have the tidal forces, right? So that is what tells you if you have really a neutron star, a black hole, or something else. So
Yeah,
5
so,
p.m. is particularly interesting.
In theory, but like,
Theory.
what level of detector do you need to be sensitive to 5 p.m. effects?
Einstein telescope will see.
So, I mean, these are even better, no? Because when you get, I mean, basically when you, sorry.
No, go ahead. Yeah.
When you get to signal polarization at 4, and for Lisa, you will have a handful of that. You should be, I mean, there's no data analysis method can go that far, but as you expect, I mean, if you just scale the statistical error of the curve of the SNR, you do need the precision. So you want to have the baseline model without the tides, so to see once you eventually have a signal polarization before, if it differs from the baseline model by how much. So yes, for Lisa and Einstein telescope, for those, I mean, Lisa and Einstein telescope, we see signals of signal and only a handful of that with that signal notification. But for that handful, you want to be ready.
Yeah, no, and so then wrap up. Told you about 3 different approaches to effective field theory and gravitational binaries. We've got self-force, which is really good for emeries. Post-Minkowskian, which scattering transient events, if you think we'll ever see those, and highly eccentric things, and also various boundary to bound stuff. Also various formal questions, and then post-Newtonian, which is the near circular, which is primarily what is used in LIGO nowadays, and is what's hopefully going to get us towards Einstein telescope, CE, and LISA. One of the nice things about having all 3 methods is, again, we have all these cross checks. Even when we don't have access to numerical relativity points, we can cross check with each other. We're all expanding the same theory of nature in the end, should all have consistent results when doing these cross limits. And yeah, there's a lot left to learn. There's a lot of very interesting stuff. This boundary to bound is very non-trivial, and there's all sorts of very subtle effects related to radiation that we're just starting to unpack. And I will say that I've swept a lot of stuff under the rug here still. So spin is something that is very interesting to a lot of people, but is a very controversial topic to some extent. And then also this question about tides and distinguishing. In these theories, you might have noticed I was using the phrase black hole a lot, but nothing that we particularly said up to now actually distinguished between anything that has mass. And so eventually you get up to the point where you get these operators that turn on that are expected to only be relevant for neutron stars or other non-black hole objects, and are expected to be zero for black holes, but we don't actually know why, and are intrigued to find out if there's some formal reason for it. And that, thank you. And also I will say, hopefully next time I talk to you, I will have comments on actual cosmology related to whether EFT and GR are equal to each other. Thank you.